So, as we settle in here, hope everybody's able to see and hear okay. We'd like to get the program started. My name is Dan Bartlett. I'll be the host this evening. I've had a long association with the mill, and my father and grandfather with the Chases and the Dennets, so it feels like home to me. And I've been involved with the board for quite some time as well. So I'd like to thank you for joining us for this third event of our series, A Sense of Place, in which we've been exploring through people, poetry, music, and history, what makes Chases Mill unique. Tonight we have a film which will give you a virtual tour of the mill, including its waterworks, a bit of the surrounding area. The footage is a bit rough in places. You may hear cars whirring by and so forth, but we think you'll enjoy it. Before we begin, I'd like to thank our videographer, Becky Howland, who jumped in to make this evening possible. So yay, Becky.
Thank you, I had a lot of fun.
Cool. So it's 47 minutes long, and at the end we will have a Q&A period with two members of our board of directors, Bob Brown and Helen Frink, who also feature in the film. Bob has been connected to Chases Mill for more than 60 years, and first as a child who took woodworking classes with Heman Chase, and today he's a retired geologist, high school science teacher, and school administrator. Since 2016, he's been overseeing the renovation of the mill with the construction crew. Helen Frink is an author and a historian, and also a retired professor from Keene State College. She serves as the chief grant writer for Chases Mill. So, a few housekeeping items before we begin. If your screen freezes up or locks up for any reason, you may want to log out and then log back in. And Brendan, our Zoom technician, will try to get you back into the event as quickly as possible. There's also a chat function at the bottom of your screen. On mine, it says more and with 3 dots. And when I click on the more, it brings me up to the chat function, and you can write a little chat that'll go directly to Brendan if you, or for whatever reason, you can avail yourself of that. So let's see, and then if there are any other additional issues and you're out of it for whatever reason, don't worry. We're going to post this on our website in probably a few weeks, so you can all see it or relive it then. So without any further ado, I'm going to turn it over to the video. Enjoy.
Welcome to Chases Mill in Mill Hollow, East Alstead, New Hampshire. I'm going to describe a little bit about the historic development of mills here and explain what a mill hollow is. Behind me, you see the historic stonework of Chases Mill. The first mill on this site was built by Timothy Delano in 1767. It was a grist mill, one of the earliest needs for settlers in the Alstead area. The dam also appears to be original, as does a great deal of the foundation of the mill and the vertical board siding and windows that you see just barely above it. Settlers came to Mill Hollow because of the availability of water power. Their earliest needs were to grind grain and to saw lumber. Roads were important to the development of a settlement like Mill Hollow. We stand at the confluence of the Forest Road, which runs directly in front of the mill, the Log Cabin Road, which is to my left, and then further on behind me and on the opposite side of Forest Road from the mill, the Prentice Hill Road and the Pine Cliff Road. Where you see a mill, you always see roads coming together. Transportation was a huge difficulty in the early settlements of New Hampshire. Bags of grain were heavy. Logs had to be sledded to the mill, mostly in winter. The earliest mill here then was a grist mill, and when we go inside Chases Mill, we'll look at the technology that drove mills like this. Everywhere in New Hampshire, our cities are built around mill settlements, from Rochester to Lebanon, from Harrisville to Keene, And most famously, the city of Manchester itself was obviously a mill settlement. Today what you see are the remaining large brick mills, chiefly textile mills. What we have here was built on a much smaller scale of stone and wood. And these old, small, wooden-framed mills are precious and rare today. To the left of Chase's mill, and using water from the same dam, stood a fulling mill, about equal in size. Fulling was a process of making wool, which was a huge industry in Alstead from about 1810 until around 1850, and then slightly revived during the Civil War. Wool manufacture consisted of several steps. Carding was one of the early steps in processing wool. The sheared wool, as it came from the sheep, was first carded by using water power to rotate two huge drums in opposite directions. The drums used for carding had spikes or prongs coming out of them, and they combed the wool in two opposite directions to pull the fibers straight. After that process, the wool could be spun, and there was a small spinning mill further down Warren Brook. After the carding process and the spinning process, the yarn or thread was usually woven at home. Home woven wool was relatively coarse and loosely woven. It was then brought back to the fulling mill. Fulling was the process of finishing home woven wool to make it more dense, longer wearing, and warmer. The wool was dumped into a tub and then beaten by huge mallets, rotated by water. It was covered with The wool itself was covered with water and diatomaceous earth made from the shells of tiny crustaceans. And this process made the wool tighter and, as I mentioned, shrunk, warmer, and longer wearing. These processes were all carried on in Mill Hollow. By 1806, the settlement in Mill Hollow was called Warren's Mills, as shown on the map. Levi Warren built this house in 1790. A prominent feature of Mill Hollows is the presence of very handsome mill owners' houses, and this was one. The lake behind us, which supplies our water, is named for Levi Warren. It's simply called Lake Warren. In the old days, it would have been called Warren Pond, a more modest title. The Warren House was used as an inn or tavern. The confluence of roads in a mill hollow made it an ideal place for travelers to stop. A mill hollow typically had, in addition to the mills, the workers' houses, one or two very handsome mill owners' houses, a public gathering space, also very frequently a store, a school, and sometimes even a church, all evidence of what had been there in the heyday of these mills, known at that time as Warren Mills, early 1800s.
Behind me is Lake Warren, or Warren Pond as it was called in the old days. And this lake was always here, but back in the time of the origin of the Delano Mill, this was called the Great Pond. And the mill was built about 1767. But 1771 or thereabouts, Israel Jones built a sawmill just below Chase's mill. And he also built the dam, which is over my left shoulder, on the edge of Lake Warren, and raised the water level about 7 feet. This gave him the original water rights to that 7 feet of water. And that also provided them to do milling in other than just seasonal capacity, because they could add water to the mill pond from Lake Warren as they needed it. But it also created some interesting dynamics among the millers as to who had control over letting the water out of Lake Warren. But that's for another time. This field behind me is where we think Simon Baxter lived. Simon Baxter was the lone person in Alstead who refused and then aggressively upheld his position. He refused to sign the association test, which at that time was required to be signed of all colonists who were backing the revolution. Simon Baxter was for the English, and as a result of this, he was jailed, and actually several attempts were made in his life to execute him, and he escaped to New Brunswick, I believe it was, someplace. But Simon Baxter, we believe somewhere out here, had his cabin or house, which is now a mystery as far as where that is.
The brick house behind me belonged to one of the most prominent families in Mill Hollow, the Kidder family. James Kidder and his son Ezra Kidder. Ezra built this house around 1830. Ezra Kidder owned several of the mills in Mill Hollow. Most interesting, well, first of all, a small spinning mill downstream on Lake Warren, and he also owned a starch factory. A starch factory used potatoes, huge quantities of potatoes, ground them, and then processed them into making starch. Starch was used on the collars and cuffs, particularly of men's shirts, and on other linens in order to repel dirt and keep them clean looking longer and a little bit stiffer. The potato yield in those days was as much as 300 bushels an acre. If you've ever dug potatoes, imagine producing a few hundred bushels, needing to dig them by hand, hauling them to a mill downstream on Warren Brook, and then having them ground into starch. Ezra Kidder became a prosperous citizen of Alstead. He was a selectman. He served as a representative to the state legislature. He redesigned the route of Forest Road, and he also succeeded in sending all of his children to college. A daughter went to Mount Holyoke College, his son went to Dartmouth College. He also was one of the first people in Alstead to own a carriage, a sign that roads were clearly getting better.
Over my right shoulder is the Kidder, another Kidder house, same family, the home of Erastus Kidder, affectionately known as Rat Kidder, and he was around in Heman's youth. And he was very sort of amused and maybe critical of these people coming up and working on the renovation of Chase's Mill back around 1914 or so. It was Erastus Kidder who was able to help Hartley Dennett and Heman in his youth to suspend all of the necessary belts and pulleys in the mill to run the waterworks. So he was an old timer, an old miller from this area, and very important in Heman's early education of water power. Over my left shoulder is what's called the Tinker Barn. Very affectionate in my own life. I have many fond memories of reading comic books as a child up in the hayloft of that barn.
We're upstairs in Chase's Mill, and we're going to take a look at some of the models that Heman Chase built to illustrate how milling was carried on here in the 18th and 19th centuries. It's difficult for us to imagine that traveling was actually easier in the wintertime over frozen snow than it was in the warmer seasons when mud impeded travel by wheel. This model that Heman Chase made is a skid or a sledge used to haul logs out of the woods. Notice that it steers. It would have been pulled by a team of horses or oxen, and notice that the runners, it seems a misnomer to call them runners, are actually heavy planks of wood. This was weighty, sturdy, and it was the best way to bring logs to the mill. Once these logs reached Mill Hollow, they would have been sawn in this kind of an up and down sawmill. We mentioned Israel Jones around 1770 or 1771, who built an up and down sawmill on Warren Brook. This is the first and simplest kind of early sawmill. Let's take a look at how it worked. This wooden piece here represents the open flume. So this carried water from the brook to the mill wheel. This kind of up and down sawmill used a very low head or fall of water. It practically sat down right in the brook. The water flowed through this open flume here and then landed on and moved the wheel. This kind of a wheel, called a flutter wheel, is kind of like a spool of thread lying on its side. It's actually wider than it is in diameter. And the motion of water on these blades, these large paddles here, turned the wheel actually fairly slowly. The mill operated at only about 30% efficiency, so this was fairly simple. As the wheel rotated, it moved a metal saw up and down. It moved up and down, sawing slowly through the log that moved forward on this kind of a carriage moved by ratchets to finally saw through the log. The story that's always told about these ancient mills is that the miller could set up a log to saw, go into his house, have breakfast, and come back before the log was sawed all the way through. Today we can see the marks of an up and down saw on some of the boards that we have here. This beam shows the marks of an up and down saw. You can see that they look to be about between 1/4 and 1/2 of an inch apart. And these were made by the saw as it moved up and down through the log. So this is one of the older pieces in Chase's mill, which is really built out of components from much, much older mills. Here you can see that there were once those wooden pegs called tree nails or trunnels through the beam itself. So this beam has been supporting Chase's mill or mills like it literally for a couple of 100 years. This is a larger model of the so-called flutter wheel used in the up and down sawmill that we just took a look at. Notice that here you can see an apron. This one's just simply made of metal. Ordinarily it would have been brick or wood in order to hold the falling water a little bit longer against the paddles of the wheel. One of the advantages of this kind of a flutter wheel is that the water goes through the wheel like this and comes out in the same direction as the stream is flowing. But the motion of this kind of a flutter wheel was simply too erratic to grind grain. So a flutter wheel could be used to power a sawmill, but it was no good for a grist mill. Now we want to take a look at Heman Chase's scale model of a grist mill so that we can see the technology that needed to be used there. Here we have Heman Chase's model of a grist mill powered by an overshot wheel. This wheel uses the advantage of the height called the head or fall of water as it strikes the wheel. The miller opened the flume. This is again the wooden flume that carries water to the mill wheel, and this lever here opens the gate to the flume, and then water strikes the top of the mill wheel. That's why it's called an overshot wheel. The buckets, and these are all made of wood, the buckets carry the water downward, and so this rotates in this direction, and you can see here the various mechanisms of wooden gears that turn ultimately the grindstones at the top of the mill. A couple of things about this arrangement of buckets. The overshot wheel was fairly efficient in that we had, as I mentioned, the weight of falling water. The drawback to it were, first of all, that it required constructing a flume high enough to carry water over the top of the wheel, and second was the difficulty in times of flood. So the spring freshet, as it was called, the spring flood, and the fall rains were good time for milling because the supply of water was plenty. The drawback of this kind of a wheel is that as it turns in this direction, rotating forward, it kind of carries the water backward in the opposite direction from the brook. In times of high water, if the water backed up against the wheel, it could actually bring it to a stop. Nevertheless, this kind of overshot wheel was fairly popular and fairly efficient. Notice that all the gearing here is made of wood. So if we turn the various parts of the wheel, as I would only do very, very carefully, we see this large gear turning, and then this kind of rotational motion in a vertical plane is transferred to rotation in a horizontal plane by this wooden gear that's called a lantern gear. And I think of that as having the kind of bars like an old kerosene lantern. So that this is the arrangement that transfers rotary motion in a vertical plane to rotary motion in a horizontal plane. Here above, we see the two millstones. And outdoors, we have a very, very handsome grindstone that we can still see. They turn with the rotation of the wheel and ground the grain between the two stones. The tongs that you see here were used to lift off the upper wheel called the runner. And the wheel every now and then had to be lifted off because the runner needed to be away in order to expose what was called the bedstone. The bedstone was the one with the grooves in it, and it did not rotate. The runner spun over it and crushed the grain between the two stones, and then the grain spread out the sides, as you can see from the grooves that we have downstairs. Notice that all the gearing on this mill is made out of wood. So a couple of disadvantages: wood wears, and it tends to swell and shrink with moisture. The advantage for wood is that millwrights were able to work with wood very efficiently, and they were able to repair their own mills. So this kind of gearing could have been replaced or rebuilt at any time by the miller himself. That was a large advantage. Almost nothing here is made out of metal. We see one wheel hub that is, but otherwise all the parts were made out of wood that the millwright would have been able to repair and manage himself. This grist mill model actually shows how the grain would have been carried upward in those little buckets that we can see and come back up to fill into the hopper and be then bagged by the miller into these tiny little sacks. The kinds of grain that were grown in Alstead were chiefly rye, barley, and corn, and wheat. Wheat had the disadvantage of being susceptible to a fungus, especially in damp or chilly weather. And with the opening of the Erie Canal in 1825, it became unproductive to actually grow wheat in Alstead or in New Hampshire generally. So the production of grain declined after the opening of the Erie Canal. This mill represents several stages of improvement over this grist mill that we've just looked at to the left. This one has the overshot wheel where the water comes in at the top of the wheel. This one doesn't show us where the flume was, but for the sake of illustration, we're going to imagine that this was a so-called breast wheel. Instead of the flume carrying water to the top of the wheel, like the overshot wheel that we just looked at, this breast wheel brings the flume of water about here. So 3/4 or 2/3 of the height of the wheel. The water strikes it here, and as it turns, the water now is propelled forward in the same direction as the flow of the stream. So this kind of a wheel was not impeded by backwater of the spring freshet or the fall rains, precisely the time of year when the miller had the most water to work with. This breast wheel also has metal buckets, as we can hear, and now we've got metal gears. So these gears would have worked a lot longer than the wooden gears that we looked at. They would have been more efficient. Of course, that meant that the miller would have had to turn to a blacksmith to perform the simple repairs. The breast wheels at the Lowell mills lasted, one of them at least, until 1890. So these were fairly efficient. They could be as large as 15 or 20 feet in diameter, so really enormous, and they generated quite a bit of horsepower. The Lowell mills, which opened in 1810, were textile mills, like the huge mills in Manchester that you can still see. And they brought about a huge change in the way of life in these small rural communities in New Hampshire because young women could now find employment away from home. The mill girls could go and live in a boarding house and be away from their families and earn some independent income. So an important stage in changing from a rural life to a more mechanized and slightly more urbanized life. Again, a breast wheel that turns in this direction, and again, a model of a pretty efficient grist mill.
these notches in the center hole here means that this stone was a top stone and it was gripped by the gears, the shaft, it's for turning. This stone is face up, this side would be down. If you lifted this stone up, and you can do that, there are two holes. There's a hole right here, and directly opposite there's another hole, and you can put pins in there and lift it up and then flip the whole stone over to put it on top in place. Right now the stone has been lifted up and flipped over so that you can see the down surface. So this whole pattern periodically gets worn off and it needs to be chiseled deeper and made into what, a sharper stone. And these, again, the pattern can either be 4 or 3, but there's got to be something to grip the stone and turn it. And it makes a great rumbling sound when it turns. The two stones can be adjusted also. The distance between the two stones can determine the fineness or the coarseness of the cornmeal or whatever you're grinding.
We looked upstairs at 3 different kinds of water wheels. First, the flutter wheel that powered the up and down sawmill, then the overshot wheel for the first grist mill model, and then the slightly more efficient breast wheel with the other grist mill model that we looked at. Now we come to see what took their place. This is a cast iron turbine that would have been used in Alstead probably any time from 1870 onward. Turbines came into use as early as 1850 or so, but they made very slow inroads into settlements like this for a couple of reasons. First of all, it's made out of cast iron. It's heavy, it had to be transported to the mill, it had to be paid for in cash, and last but not least, the miller himself could no longer simply repair it by using his spare pieces of wood. So these cast iron turbines came to be used in Alstead in the second half of the 19th century, and over time they replaced the overshot and the breast wheels that we've been looking at upstairs. These powered the sawmills and the various woodworking mills that worked further down on Warren Brook.
So this is our exhibit turbine. It's not exactly like the one we have downstairs. This is an 18-inch. We have a 21-inch downstairs. This casing is, the scroll casing here is what this piece goes into. So this whole piece lifts up and it rests inside this casing. The water comes in through the penstock in here and is controlled by a gate that's lifted up or down to let the water in or out. It spins on actually a wooden bearing made of a type of wood called lignum vitae. It's the hardest or heaviest, densest wood in the world. It's a very oily wood, and so it's self-lubricating. In fact, even some of today's naval vessels still use wooden bearings in the propeller shaft support system. This little turbine over here in this table, and let me put it back together a little bit, used to be like this, and the blades went up and down in it, but you can see it's totally rusted out. And this little turbine was 9 inches, and we've restored what was left of it, and I'll show it to you when we go downstairs. It also spun on a piece of lignum vitae. This is a little piece of that wood. It sinks like a stone in water, very heavy, and is the main support system for the whole cast iron turbines, shaft, everything. So that takes a lot of weight and a lot of wear. The water hits the blades on this turbine, but as it exits, the water goes out the bottom and is pushed to the side by the configuration of the blades on the bottom. And that puts a force, a lateral force, a torque on the turbine, spinning it around, and that's what spins the shaft. And this main shaft, the vertical shaft, goes up and is connected with the rest of the millworks, which I'll show you downstairs.
We have 3 of these turbines, a 21-inch Wetmore turbine downstairs, this turbine which is 18 inches, and a 9-inch turbine downstairs which you'll see running the hydroelectric system. These turbines, all three of them, were manufactured in Claremont, the Sullivan Manufacturing Company. And that's of interest because, as I mentioned, turbines were expensive and they needed to be transported to the mill. They had to be paid for in cash, and the miller could no longer repair everything himself. So it was important to get turbines from fairly close by. The city of Claremont has a huge complex of brick mills, and it's therefore perfectly logical that these turbines were manufactured right in Claremont itself.
One of the things, I'm going to digress a little bit and get into something that fascinates me about this mill and about milling, and that is the simplicity of the tools that these people came up with and that they used for their work. So just to remind us of the basic, simplest tools, you have things like a lever, and a lever is just turns around a fixed point and is used to pry things. You have wheels and axles. You have wedges, which can be combined on two sides to make an axe, a cutting blade. And the settlers who came up here in 1753 to Alstead, there were 8 men who came up as a group, and they found a meadow that was cleared naturally. There was grass there, they had oxen, and they had simple tools with them. And they were here 10 years before this was a chartered village. They cut wood, they cleared land, they built some log cabins, and it was probably a year or two before they brought their families up into this area. These men would have expended energy that was used to support their bodies, say 2,000 calories a day, but they also would have expended energy in making tools that they used, simple ones. But they didn't use much energy. They got along really well. If we go back even further and look at humans and their tools, here's a very early tool used for grinding grain, just a rock and another rock. And you can take these 2 rocks and you can make a reasonable flour out of them. This didn't take up much energy. And what I'd like you to think about as we look at some of these tools is how they get put together in larger and larger combinations that use more and more energy. And so you have to have a source of the energy. You have to harness energy somehow. So this has got levers, it's got wheels, it's got wedges in it, and this is a device that's used to fasten the belting of these. This material here is a belt that runs around the machine, and this tool is used to lace. It's called lacing because originally they used to use leather lacing in here to lace this together and make a belt that can then run around wheels, transferring force from wheel to wheel. So these early settlers were creative, they were industrious, they were inventive, ingenious, and I'd like to show you just the kind of thinking that I find fascinating that you'll see throughout this mill and throughout the early development of industrial machines. Okay, here's a charming use of inventiveness, and this was done by Heman Chase. This is a drill press. It's an old drill press. It's run by a belt around a wheel, and that goes to another pulley, and it goes over to another pulley, and there's another belt, and ultimately it goes over to an electric motor. But the switch is over there, and I can't reach it. So Heman, working here at the drill press, obviously thought there was a better way. How could he turn the switch on, which is over there, from over here? So what he did is he put a piece of wood in here, which is a little lever. I can move this little lever back and forth, transfer the energy along this piece of wood to another lever. Here's another lever, goes back and forth. The energy comes down the iron rod, which is just bent at 90 degrees. The other end is bent at 90 degrees as well. And now the switch moves back and forth. This is his version of a remote control. If you have to turn it on from over here, you can just pull the switch and it turns it on. And it's nothing more than mechanical combination of simple machines. But if you look at some of the complex machines in here and take them all apart, you'll find out that they're made of simple machines, simple components. It's the ingenuity and the creativity that's really interesting. Even the gears. I'm looking for a set of gears. I'm looking over here. Can we go look at this gear here? Even a set of gears like this, these are cut as wedges. So you not only have a wheel and axle, the wheel itself, but the beveled gears that allow the sliding and meshing together of the gears is also an application of simple machines. Now this mill did not use gears because if you get caught in gears, it's really ugly. But this belt, the choice was made to run it off of flat belts and pulleys. And it was viewed as a much safer mechanism to use. All right, here's a combination of simple machines, inventiveness. This is a homemade lathe, but it's a treadle lathe. It's powered by human power again. And using human power, you can only go so far. But this is a way to use machines to add to your power and add to your ability to turn objects like this round object here, or you could turn table legs. This is a table leg that was turned on a lathe, and do other fancy work with lathes. This one's powered, however, by your foot, and by pushing down on it, and then getting the rhythm right, you can just keep working it with your foot to spin this around. Now lathes, operating lathes, they call it turning the wood. And then you can take your tool and you can begin carving. The trick is you can't stop to think about your foot. You've got to think about your foot and the chisel. So it's a little bit challenging, but I suppose if you use it enough, you can become very comfortable with it. But of course, they have to turn the round handles to the chisels with a lathe as well. And my point is that as you make machines more complex, they require more energy. Your life and your daily existence demands more energy. And so when they found running water coming down through Warren Brook Gorge, their response was power. They saw power, and they saw that ability to start manufacturing, and that's the whole story of the early industrial revolution. Okay, here we are at the heart of the millworks, and the whole joy to the settlers of this water was power. Here we have water coming in from the mill pond and dropping 15 feet through a 20-inch pipe. Now that 20-inch pipe weighs, the water in that pipe weighs about 130 pounds per foot. So if you add that up at 15 feet, you come up to something like a ton of water by the time you get to the bottom. And all of that is being pushed against the blades of the turbine. So here we have a long pipe, 20-inch penstock, sometimes called a flume, goes from the mill pond, drops down to the turbine, which is that snail-like curled structure down there. And the water is controlled with a gate. This gate is called the star wheel. We call it the star wheel. Interesting little side story was that Heman Chase saw this being made when he was a teenager by Erastus Kidder that we mentioned earlier, who turned it on a lathe in his mill down the brook. Heman never ever dreamed that he one day would be owning that same star wheel. So this star wheel turns a rack and pinion gear, which lifts the gate, which turns on the water. Now when that water hits the turbine and starts spinning the shaft, this is the shaft. This is going to start spinning right here. This is a pulley called a drive pulley on the shaft. The belt will transfer its energy to another wheel across the room. And to keep the belt taut, tense, there are a couple little helper pulleys. There's a little helper pulley here that keeps it from dropping off. But for those of you who like to know a little bit more about the physics of things, a lot of people wonder why a flat belt doesn't drop straight off of a flat pulley. The reason is this pulley isn't flat. The pulley has a curved surface, slightly crowned surface. So the center of this pulley and all these drive pulleys is slightly greater diameter than the edges, meaning that the force of the belt against it is slightly greater at the fatter part. And the belt wants to move to that place where it grips best. So if the belt is low, it'll move up. If the belt is high, it'll move down to that point on the pulley where it grips best. That force is going to be transferred all the way across the room to what's called a line shaft. That's a long, 30-foot long, 2-inch thick, solid piece of iron that has a variety of pulleys on it. That's going to start turning, and on some of those pulleys, we're going to hook up machines. And I'm going to show you about that in just a minute. But let's take a look at the turbine running, and then we can look at that other stuff. So here I'm lifting up the gate, and what I want you to watch for is this begin to turn. There will be a force of torque on this, and that will transfer its energy over to those other wheels, which of course will build up momentum and develop quite an enormous amount of force. So the water is coming out down below. We've watched water turn wheels and turn turbines and do a lot of work. This is where the water exits the mill. It's called the tail race. And the water would run out the tail race after it was used, and it would be used by the next mill down the stream, and then the next mill after that, and just keep getting reused. Gravity's just constantly pulling more water down. And here we had 5 mills within a quarter of a mile, all using the same water. Okay, here we are fighting the noise of running water. I hope you can hear me okay. This is the small 2 horsepower or 9-inch Tyler turbine that we showed you upstairs that was all rusted out. Inside of this is the blades that were all rusted out upstairs. This was also probably made in Claremont, New Hampshire. We don't know for sure. I'm going to open it up and the water will spin that turbine. That's going to spin the shaft. And when the shaft is spinning, that's going to turn these pulleys. Now I have 3 pulleys. There's a flat belt pulley, and there's a wooden flat belt pulley, and there's a V-belt pulley here. These are going to go over to a counter shaft because I need to speed it up. Here I have 560 RPMs, and I want to generate some electricity with a car alternator, which requires about 3,000 RPMs. So I need to take the speed of the shaft around a little wheel, transfer it to a slightly bigger wheel, and then transfer that to a slightly smaller wheel, and here I can get up to 3,000 RPMs using this combination of 4 pulleys. Part of the interesting thing in engineering in these mills was to design your pulley sizes to get the number of revolutions per minute or RPMs that your machine needs. Now here I want to generate electricity with a car alternator. So I'm going to turn this on. It's going to spin the alternator, and it's going to store the energy in a deep cell battery over here, marine style battery, 12 volt. And this is how we're generating our electricity for the bottom 2 floors of the mill. And we're also doing some educational project work with 12 volts as well. And that's why we have this system running alongside the bigger system. So I'm going to go open this up. I'm going to get wet if I stay here. This is telling me what our output is here in volts in red for charging. Okay, this is a little toy Pelton wheel. And it's the sort of thing that's a lot of fun to do as project work. This is fed with simply a siphon through a garden hose, and I'm going to turn it on, and the garden hose will shoot water against the little metal blades on the Pelton wheel. So that's your energy source, and then you have a takeoff pulley which you then can decide what you want to do with, but you've got available energy here. And of course, it's energy that's not coming from your own muscles. Okay, we just saw that this little 2 horsepower, 9-inch Tyler turbine is generating electricity for us. But we also want to use some of its energy transferred by this flat belt over to this counter shaft or jack shaft over here. And this shaft is going to spin another pulley down at the other end, which is connected to an old car generator. Heman used to show this as how he generated electricity. So we want to try to get it working again. Cars don't have generators anymore. They're hard to find. So this is the same generator that Heman used. We've had to remagnetize it and do some other things to it. And we're going to see if we can make it generate electricity for us once again by taking energy off of our little Tyler turbine. I'd like to mention, I spent my life in education. I taught science, and everything that you are taught very often leaves out the work of having achieved whatever discovery was made. I'm having trouble right now trying to solve this problem. In order to generate electricity, I have to get that generator up to 1,800 RPMs. This is a wooden pulley because it's a pulley I made upstairs on the lathe, and I need to find an appropriate size of the pulley, and I need to find out how high it has to be relative to that pulley so that it won't slip off. So this is a process of trial and error, and I've made many trials and failed many times, and I'm continuing to get closer and closer to the answer of how this will work. But it's important to understand that these things don't always work the first time through. You try and you fail and you study the problem and what went wrong, and then you come up with a new model or a new pulley, and then you try it again. So right now we're still working on getting the generator operating because of a difficult case of alignment with our pulleys, which are rusted together. So we're not able to move them. It's creating some challenges. I'm sure we'll solve them, but it's important to realize that things don't always go well the first time.
that was amazing. Really well done, packed with information. Outstanding job. And at this time, I'm going to open it up to Q&A with Bob and Helen. If anybody wants to ask a question, I think you can raise your hand. I think there's a way to raise your hand. I'm not sure how it works. I think you do it on the, oh, maybe not on this program, but.
Participant feature.
Oh, participant. Yeah. Well, anyway, I think Bob and Helen know how to handle the Q&A. So take it away, Bob and Helen, and feel free to ask questions.
Are there any questions?
Squire Brown.
Hi, Squire.
You have to unmute.
Are you unmuted?
Yeah. Okay. Have you figured out an equivalent horsepower for the water turbine?
Well, we have three calculations on that. Two are historical from Heman. He has mentioned in two different locations that it was 10 horsepower, and then I think there's a place that says 12 horsepower. And then I think maybe Helen might have found some of the original paperwork for a turbine that size that had horsepowers up to 17, I think, listed.
What I have is a booklet published by the U.S. Geological Survey in 1906 that gives statistics for all of these turbines. So it tells us the horsepower of everything we've got, where they were made, how many RPMs, and so forth. I'm a person of the book. I don't know how these things work the way that Bob does, but I can tell you what I read in the historic documents. So that's my source of information. Ask Bob for how it works. Ask me for what it says in old texts.
Very good. Thank you.
One of the problems with the turbine's efficiency is that they have rusted to the degree that the clearance of the components, that inside piece that spins around is called the runner, and the gate that lifts up and down has corroded and it doesn't fit real tight. So sealing the space between the moving components and capturing more of the energy of the water is a challenge with these older turbines that have experienced so much rust. Our runner was coated with a number of layers of an epoxy compound and in hopes of closing up the gap a little bit. It had a registered RPM rating. I think Heman said it ran around 375 RPMs, and I've run it up to over 380 RPMs since we put in the restored turbine. But they are not likely to perform exactly the way they were touted to in their books of days gone by.
I remember Heman taking me down into the basement there and showing me how all this works, and I didn't have a clue. I was only like 10 or 12. So thank you so much for helping me to understand the water works.
You're welcome. I also experienced it at under the age of 10. I think in 1953 or so, my family was invited in by Heman, and we walked down through floor after floor, getting deeper and deeper, and it was a really mysterious and kind of spooky place. And over time, I certainly didn't know anything about the mechanics and how it worked or any of the engineering stuff, but it became a place that had an atmosphere that I always gravitated toward. I just love the smell of walking into that old building.
Yeah. It seemed to have Heman's heart in it.
Mm-hmm.
I have a question. Can you hear me?
Yep.
Okay. What effect did the flood of 2005 have on the mill, the Chase Mill?
Okay. That flood, it's just amazing that the mill was spared to the degree it was. The flood waters in that flood were 2 feet higher than the main floor level, and the water was pushing against the outside of the building and did not dislodge it, and it did not change the dam at all. It did, however, do some scouring. Some of the brook below the dam was scoured, so the foundation started to become undermined slightly. Then some of the water ran down through under the middle of the brook and started to remove a lot of the fine material that's mixed in with the rock material in the foundation. And then a third track of water went around the inland side of the mill and created about a 4-foot deep gully that ran around there. Miraculously, there was almost no damage to the mill. It couldn't be repaired with a little woodworking along the front of the mill, repairing the sill, and then we did have to go in and do quite a lot of work with the foundation with a specialist dry mason. But it was very, very lucky.
Wow.
I'd like to add a different kind of answer to that question, and simply say that the flood of 2005 was devastating for the foundations of these old mills. The foundations of old mills and the mill dams used to be far more visible before that flood struck. I live in East Ackworth, and I'm surrounded by mills, and there were mills all up and down the Cold River, and what you could see before 2005 is gone now. And that's one thing that makes Chase's Mill so precious, is that we still have it, and we still can see what was there. And one of our plans for the future development is to clear out and make accessible a path down Warren Brook so that people can see what was left or what remains of these old mills, and using signage and placards get a clearer idea of what actually stood there before these floods hit. So there's a much larger story to be told than you can actually see today. And Chase's Mill is a treasure for that very reason, but we want to also be able to commemorate and show a little bit more of what has been lost there.
That's
And
a wonderful idea.
One of the things we did lose was a considerable amount of the Israel Jones sawmill that was located about 100 feet on the other side of the brook and below Chase's Mill. And the stonework that was left behind from that mill suffered terribly. And I would make a rough guess that maybe close to 50% of the existing foundation was removed in that flood. That little stream that came down below the Chase's Mill, Warren Brook, was judged by the Army Corps of Engineers to be 7 feet deep during the flood.
I'm a teacher, and that what you just described, making the signs and placards for the old mills, that sounds like a great school project or service learning project that our school could do.
Yeah,
possibly.
That'd be great. I'm going to just point out that it is 8:30 and our presentation is officially over, but I think Bob and Helen are obliging to stay around for a little while, and you can too, and we can continue the event. But if you'd like to check out, that's fine too. And as I say, this this presentation has been taped, so the whole thing is going to be available on our website in a week or 2 weeks or so. So if you missed anything or want to see it again, it will be on the website. So we thank you all for joining us tonight, and stay tuned for the next event, and we can continue Q&A for as long as you want. Thank you.
I was thinking as I was watching this about History Camp in Boston every year. They have a Saturday that's set aside with history buffs from all over, actually around the country do come. And they have hour-long, basically, presentations about all different kinds of history, American history. And this would make a wonderful presentation for that. It would get you a lot of visibility. This year's was canceled. It was supposed to have it in March, and then it's at Suffolk Law, Suffolk Law in Boston. And it was canceled this year, and then it was supposed to be in July, and that, COVID. So, but I would think looking forward, this would be a great time to get some more publicity and get some more eyes on your project.
Thank you, Jeannie. And
Thank you.
you and I can be in touch and talk about that off screen. That's a wonderful, wonderful idea. Good to hear.
I have a question. Why did the Erie Canal shut down? What was the effect? And why did that?
Let's get out of there.
Sally, this is my sister asking about the Erie Canal and what happened. The Erie Canal made it so much cheaper to transport grain east than it had been in the days before water transportation. Erie Canal predates railroads, and so it was easier to transport the grain eastward from the Midwest than it was to grow it here. One of the problems, especially with wheat, was that it was susceptible to a fungus called blast. And people very often had the familiar to farmers experience of a whole lot of labor and not much produce. So what remained grown here was mostly barley and some rye and corn, used chiefly for cattle feed, but wheat pretty much went out with the Erie Canal.
Thank you very much. This was excellent. Tremendous treat.
Thank you.
I had a question. I mean, one of the things that seems apparent here is that the viability of a mill depends on a big vertical drop that you can harness into energy. And I noticed that we were in Austria a while ago, and they have all kinds of mills. And of course, in the Midwest, which is flat, having been sheared off by the glacier, there are basically no mills that I've ever heard about much. And so I'm wondering if the mills in Austria, for example, were lasted longer than in, for example, New Hampshire.
Helen, you want to try that one? I don't think I can address that very well.
I don't know as much about that as I should. One of the big differences was, what did people need to mill? And in many of the European countries and in the Midwest, there was not the amount of timber that we have here. So New England is very rich in timber, meaning lumber, and so the need to process wood, I think, kept mills going. We're institutional members of the Society for the Preservation of Old Mills, and their website is just spoom with a SPOOM.org. And most of the mills that they profile are grist mills, as it turns out. And most of those are in places like Pennsylvania, North Carolina, Kentucky, and so forth. So it really depends on the product that people are trying to process and the availability of water. Bob mentioned earlier something about how small the stream of Warren Brook is and all the mills that existed there. And one of the points I always try to make is that the oldest mills ran on small streams. Damming up the Connecticut River to produce the mills that we see in Bellows Falls was hard. And damming up the Merrimack River, for example, or the Merrimack River through Manchester and through Lowell was difficult. But damming up Warren Brook didn't take very much labor. So the oldest mills are on the smallest streams. And what people looked for there always was a narrow gorge. So not a place that could be utilized for the maximum of power with the least amount of labor. That kind of determined where people tried to locate mills.
There's been a lot of, as you can imagine, a lot of experimentation with different types of water wheels. Heman experimented with quite a number of them, and he made models of them. One of them is called a Pelton wheel that you can buy online today, and it's has a series of cups around it, and it's able to operate on a low volume of water, but it needs a very high head, that is the drop of the water, so that you can, in a flatter area, you can use a very small stream, but you have to run quite a long line of tubing, or the penstock, or the flume, whatever you want to call it. It has to be rather long, and then it gets smaller in diameter as it approaches the Pelton wheel. But it can be used to do things like generate home electricity, a small project work, and whatnot.
Bob, one of the things that I remember when I was first there as a kid and Heman turned it on was the belts flapping away and making a lot of noise. And I've always wondered what happens when a belt breaks.
Oh, I can tell you because I learned how to make the belts with that belt lacer that was in the video, which was donated by Peter Rhodes. It was his grandfather's. And so I've had belts break in a variety of ways, and they generally just drop straight to the ground, right where they are. They part. The old leather belts are made of many, many sections that have been feathered carefully and glued one string to the other to make these long belts. And the ones that were remaining in the mill were in very bad condition, but I did find a few and I did try them, and they did break within 10 minutes of use, I would say. And they typically just drop to the floor, as did the canvas belts, just drop where they are.
How long does a canvas belt last?
How long?
Yeah.
I don't know, but what's interesting is when we went to find belts, of course you're networking with people who are in the business of old machines and whatnot, and so I was led to Page Belting in Boscawen, I think it is, New Hampshire. They, I think, were once the world's leading producer of flat belts, and they're still in business. And so, very nice guy who I visited with on the phone, and he explained how the leather belts were made, and he talked about the history until I kind of had to let him go because he had work to do, I'm sure. But he does entertain tours and whatnot. They're over 100 years old supplying belting, and they're still doing it now.
Mm-hmm.
I have a question. I don't know if I'm on speaker or not, but
yep.
I remember in about 1960 or 61, there was a logger named Wally that rented the barn from Mary Burroughs.
Yes.
And he used to log with a sledge. Once he let us come along with him, and it was a violent thing. These two huge Belgians, Ginger and Lady, I don't know why I remember that, pulling this sledge with logs on them. And I wondered, well, how far could he go with that, and where was he going with the wood? Does anybody remember that?
I remember it very well. I used to follow him into the woods when I could and watch. He was actually logging not far from the log cabin, which is owned by Dan's family. It was owned by Dan's family, and he was riding the. He called them a scoot. I think they called them scoots. That's the name I remember for him. And he'd climb up on top of the logs and kind of straddling the logs, and if it wasn't too dangerous, a stretch of road, and I'd forgotten the names. Lady and Ginger, was it?
Ginger was an older horse.
Lady and Ginger.
No, Lady was the older. Lady was the one that kicked.
But I used to ride those workhorses.
Yes, he used to let us ride them to water. After he came in, if we were there at 5 o'clock, we could get on the horse without the harness and, you know, wind up the reins and then ride them to where the road came to the river so they could drink, because there was no water in the stalls. They were just tie boxes.
Yeah.
And sometimes we slept in the barn, and there were 2 other horses there that weren't used anymore. But I remember loving to ride them to to get water. Lady was much easier to ride because she had a more collected trot, but she kicked, so you had to be really careful getting her out of the stall, whereas Ginger was friendly and didn't kick, but she had a really long trot that would bounce you right off.
Yeah.
I put a side saddle on Ginger and used to take her out into the woods and ride her with a side saddle. It didn't have any stuffing. It didn't have any stuffing in it, so I could just put some burlap bags on her back and then put the old side saddle on her, and I would hop right up there and off we'd go into the woods. It was great fun.
I remember riding around the lake, but I remember falling off Ginger a few times. But what was your name back then?
Taffy.
Oh, Taffy. Oh, for heaven's sakes. Are you all here? Taffy, Bossy, Tub, and Bo?
Nope. Just Tub and myself.
Who is Tub?
Bob.
He's Bob.
Oh, I'm sorry. You know, all I can remember is Bob was your dad.
Yep, and this is his son.
Well, it's hard to remember. I'm Pat Spur, by the way.
Yeah, Bo's here.
Here a few summers.
Bo's here too. He's online too.
Oh, hi,
now
Bo.
those horses stayed in the Tinker barn.
Yeah, it wasn't called a Tinker barn. It was just Wally's barn.
Yeah.
And sometimes he'd let us sleep in the hayloft.
Yep. It was also called the horse barn. I used to call it the horse barn. I spent all my summers there.
But remember, we used to ride the horses to water.
Oh yeah.
Came in?
Oh yeah.
That was so much fun.
Yeah.
Your phone is ringing. Yeah, I'm here. I don't know if I'm muted or not.
Yeah, no, I can hear you. Hi, Bo.
Hi, Bo.
Great.
Hi, Bo.
Great.
It's hard when you have adult names and you're not used to adult names.
I think Bob,
I remember when Taffy was trying to look like Vera, and you had a signature all worked out for your stills.
Yeah.
Like Vera's. I can't remember Vera's last name, but the artist.
Yep.
Yeah, that was good times. We're still in contact with Ione, who was also artistic. I don't know if you remember her. A family friend.
I remember the name. Yeah.
Yeah. Well, it's good to see everybody.
Yeah, everybody.
Hey, Bo.
Yeah.
Hi.
We can't make this a family program here.
Hi, Ludi.
Nice seeing Squire.
Hi.
Well, I think if we're probably about time to close up shop for today. If there are any last questions, we can quickly take care of that. But otherwise, I think we're going to unplug and call it a night.
Thanks so much. It was a great presentation.
Thank you, Dan.
Thank you.
Thank you, Dan. Thank you, Dan.
You're welcome. Thank you all for